All right. Okay, let's come back to how do we name this particular compound. All right. So you have 5 carbons in the long continuous chain. So the parent compound is pentane. You have uh, so you have to number it from here. If you number it from right to left, you'll give this number four and number 3, so that you want to give it the smallest location numbers. So number it from left to right. So this would be the second carbon. This is the third carbon. So 2-chloro, 3-methyl pentane. All right. Alphabetical order. So chloro comes first, followed by methyl. Okay, so between a number and a letter, there has to be a hyphen. So 2-chloro hyphen 3-methyl pentane. Okay. All right. Next, we come to cyclic alkenes. All right. Cyclic alkenes with substituents. Now, you want to go have the substituent the smallest location number. So you're either going clockwise or counterclockwise around the ring in order to give that substituent the smallest number. If you have one substituent, it automatically becomes carbon 1. All right. So wherever it's located, that substituent, that's carbon 1. So you don't have to give it a location number. If you have more than one substituent, then location numbers are needed. All right. So this is simply called as ethyl. Ethyl because there's 2 carbons in the substituent. The long pair, continuous carbon chain, of course, is the cyclic structure, cyclohexane. So it is ethyl cyclohexane. All right, so when you have halogen atoms, they're replacing basically one of the hydrogen atoms. All right, you have to number them in alphabetical order. So for example, bromo will come before chloro, will come before and then followed by fluoro and iodo and so on. Right. So also it's numbered according to where it is attached. All right. So you want to make sure that you give it also the smallest location number. Right. So when you have methane, one of the hydrogens replaced by chlorine becomes chloromethane. You don't have to give any location number. There's only one carbon. When you have a bromine replacing one of the hydrogens in ethane, all right, you don't have to give it a location number because that wherever this substituent is becomes carbon 1. All right, so bromoethane. Okay, now here, because there's 3 carbons and that fluoro is in the middle, therefore you have to give a location number. So it's 2-fluoropropane. Similarly here, because the chlorine is the long continuous chain is the 3 carbons, and then you have a chloro on the second carbon as well as a methyl. All right, so alphabetical order 2-chloro, 2-methyl propane. All right, so when you're given the name and asked to draw the structural formula, first draw all the continuous carbon chain. All right, number that chain, and then you can place the substituents wherever you wish so as they get the lowest location numbers. All right, and if you just do the condensed structural, you don't have to do the expanded, and just put in the correct number of hydrogen atoms so that each carbon always forms 4 bonds. Okay, so break this down. 2 comma 3 dimethyl. All right, that means there's 2 of those metal, one at carbon 2 and one at carbon 3. The parent compound is butane. That means you need 4 carbons. Okay, so you can either do it to generate a condensed or the line structural or both. Okay, All right. Then you know that at carbon 2 and 3, there are methyl groups. All right. So fill that in, and then you can fill in the hydrogens because end carbons will have 3 hydrogens. Now, carbon in the middle has only 4 bonds. So it's attached, each carbon is attached to 3 other carbons. So it'll only have 1 hydrogen each. All right. So this is going to be CH3, CH with the branch CH3, CH with the branch CH3, and then CH3. All right. And then, of course, you can go about doing the line structural formula as well. Okay. Okay. So this would be 2,3 hyphen dimethyl butane. Okay. All right. Draw the condensed and line angle structural formula of 3-bromo-1-chlorobutane. All right. So the line structural formula is already given. Butane means there's going to be 4 carbons, so 1, 2, 3, and 4. On chloro has to be on the first carbon, so it's attached over here. All right. And then on the third carbon is the bromo. All right. So therefore it's attached here. All right. And it's in alphabetical order. So 3-bromo, 1-chlorobutane. Okay. And then you can go about filling. So this carbon will have 2 hydrogens. This will have 2 hydrogens. This will have only 1 hydrogen. And this will have 3 hydrogens. Okay. So 3-bromo, 1-chlorobutane. Okay. So name each of these following alkanes. All right. So you want to give it the smallest location. So count up the number of carbons: 1, 2, 3, 4, and 5. So pentane. So 2-chloropentane. All right. Again, long continuous chain. So 1, 2, 3, 4, and 5 pentane. All right. At carbon 2 and 3, there's a methyl group. So it's going to be 2, 3 dimethyl pentane. Okay. Okay, coming to section 12.4, some of the properties of alkanes. Well, you know that they're insoluble in water. They are low density. Think of oil, it's less dense than water, floats on water. The alkanes from 1 to 4 are gases. So methane, ethane, propane, butane are gases. All right. Once you go beyond 4 carbons, they kind of become like liquids. All right. Oil-like properties. And then as you go higher, they are solids. So all those wax, etc., that those waxy coatings on fruits, they are the solid alkanes. Okay. All right. So as you can see, octane, all right, 8 carbons, that's gasoline. All right. So it's a liquid at room temperature. Okay. So 4 carbons are gases at room temperature. Between 5 to 8 are volatile. Volatile means that they easily evaporate. All right. Doesn't take much. They have very low boiling melting points. They have low boiling points, so they evaporate quickly. And then they are also combustible, so they're good for as fuels. Okay, because you can burn them to generate energy. Okay, so pentane, hexane, heptane, octane. All right, octane. And you may or may not have heard about the octane rating of gasoline fuels. All right. Okay. So again, this is the line structural formula of octane with the 8 carbons. Okay. Now, once you go beyond 9 carbons, 9 to 17, They are liquids also, but higher boiling points, like the motor oils and the kerosene, diesel, etc. All right, 18 and more, they're called as paraffins because they kind of like wax at room temperature. So Vaseline, wax, those are basically hydrocarbons with a lot of carbon present, a very long chain carbon. All right. So the melting and boiling points are very low, which is why they're volatile. They are able to kind of be evaporated easily and so on. Okay. The bonds are non-polar. They have dispersion forces. All right. So van der Waals or dispersion forces, and especially because of their structure, the way they are packed together so tightly, the longer the chain, the higher the dispersion forces. All right, okay. So longer chain alkanes have higher dispersion forces because there are more points of attraction between the molecule. All right. And that is the reason why they are more compact. They're either in the solid and the liquid states, whereas the smaller alkanes have less dispersion, so they are gases. Okay. If you take a long chain alkane or a branched alkane, you will, if you compare the boiling points, you'll see that the branched alkane has a lower boiling point compared to the unbranched alkane. All right. The more the number of branches, the lower the boiling point. All right. When the shape is kind of linear like this, they stack well. The molecules have more points of attraction, they stack well. Kind of think of it like stacking saucers, all right, or plates. Whereas if you have like something like an obstruction, it's hard to stack them close, all right? They don't fit together as closely because there's a lot of space between the individual molecules, all right? So it's easy then to boil or melt them because they don't have as many points of contact. Okay. So cycloalkanes have higher boiling points when you look at the straight chain alkanes, all right, with the corresponding same number of carbon atoms. Okay, because of the fact that the cyclic structure is very rigid, all right, there's free rotation in the straight chain, all right, because the carbons can freely rotate around and form different conformations, whereas the ring structure is kind of rigid. um, and so, because of that rigidity in the structure, the rings can then have more point of attraction between the molecules, and they can be stacked more closer than even the straight chain alkanes, all right, which means that they have higher boiling points. Okay. So if you compare just a straight chain alkane like pentane, a branched alkane like 2-methylbutane or dimethylpropane, and the cyclopentane, right? So they all have 5 carbons, okay? And then if you compare their corresponding boiling points, you see that the pentane has the highest boiling point, followed by the normal pentane. All right. The more branches, the lower the boiling point. Okay. So alkanes undergo combustion. Basically, you burn a carbon hydrogen compound in the presence of oxygen. You get carbon dioxide, water, and a lot of energy. Okay. So whether it is any of these, you can burn them, and then all you have to do is balance the reaction, make sure that the numbers of carbons and hydrogens and oxygens match up. All right. Always start by balancing the carbons, followed by the hydrogens, and last by the oxygens. Okay. So here you have methane. Okay. The balanced reaction is 1 carbon dioxide and 2 waters. All right. Okay. Propane, this is incorrect. It should be C3H8, would require 5 oxygens, 3 carbon dioxides, and 4 waters, would form. All right, so you're quite familiar with the balancing. We'll stop here and continue this in the next video.